Hello, everybody, and welcome back to another Geography 340 Climatology lecture. I am Dr. Zach Hilgendorf, and today we're going to be talking about latitudinal variations in the global energy budget. In the last few videos, we've been talking about that global energy budget, where it comes from, how much comes into our atmosphere versus how much is emitted, where it comes from, etc. So if we recall in our last video, the radiant energy input into our Earth system is about 1.734 times 10 to the 17th watts, or averaged over the surface of our planet, 341 watts per meter squared, meaning that our radiant energy out is 1.734 times 10 to the 17th watts, or 341 watts per meter squared. If you recall, that drives at our thermodynamic equilibrium. We need that balance of energy in to energy out. So we often have to think, well, we've got more radiant energy coming in to the center of our planet, but we've actually got less radiant energy coming into the poles, right? We modeled this in our total daily insolation. So the energy coming in between 23.5 north and 23.5 south are tropics, Tropic of Capricorn and Tropic of Cancer. They receive a lot more insolation, incoming solar radiation, than do the poles. So averaged, we talk about 341 watts per meter squared of insolation averaged over the planet, but there are latitudinal variations in that we need to consider. And radiant energy in exceeds radiant energy out along the tropics or between the tropics, versus the poles where radiant energy out exceeds radiant energy in. And that flux point, if you will, that tipping point, is right around 35 degrees north and 35 degrees south latitude. So it kind of looks like this next diagram here, where we can see around that 35-degree mark, our annual outgoing radiation exceeds annual incoming radiation in the northern portions, or north of 35 degrees north if we're in the northern hemisphere, for example. Whereas in south of that, between the equator and 35 degrees north, annual incoming radiation exceeds annual outgoing radiation. You see, here's that line that kind of shows where those kind of meeting points are. So here we can see a little bit more finely the average daily net radiation at the top of the atmosphere. This is some data from the Earth Radiation Budget Experiment, or ERBE. We can see the scale on the bottom there. This is in watts per meter squared. So we can see below or negative 100, or greater than negative 100 or less than negative 100 in the purple colors. So basically there we're seeing a loss of energy versus a increase or surplus of energy. Along the equator, we see greater than 80 watts per meter squared. So we're seeing a surplus or greater energy than is coming in. And start to maybe see some trends here that are related to things like the equator and continents and our major oceans. Latitudinally, we can see variations based off of how far you are from the equator. And there are some kind of central points where you're seeing surplus, like the ocean between South America and Africa. We're seeing kind of a bulge in energy there, watts per meter squared. So we see that 77.4. And think of this kind of like a contour map. You see kind of this contouring effect across the map here. And then in the Indian Ocean, we see kind of the peak, or almost the peak, and along that portion of of Oceania, like the Pacific, South Pacific and all that, we see 88.3, kind of a high point over there that extends a little bit south of Hawaii um, and Thailand and all those areas. So we can kind of get a better idea of what this net radiation looks like distributed across our planet, not just in a latitudinal sense, but there are other drivers that affect that radiation distribution. So here we can see kind of using some shading to show what that looks like. The redder portions or along the equator are seeing more insolation and net radiation than the poles are. So based off of this differential heating and cooling portions of our atmosphere, the net energy in and the net energy out, we have different movements of air mass throughout our world. So we get things called advection, right? So advection refers to the transport of something from one region to another. As far as we're concerned, advection occurs anytime an air mass moves. So when an air mass moves into an area previously occupied by a cooler air mass, so when warm moves into cool, we have warm air advection. Likewise, when we have moist air advection moving into an area of, or when we have moist air moving into an area of drier air, we have moist air advection. Flip-flop. We have cold air advection, which happens when cold air is moving in and replacing warm air, and dry air advection, kind of the same thing, when you've got these drier polar air masses moving in and bringing drier air down to the mid-latitudes and tropics. So meteorologists are most concerned with advection of variables like temperature, moisture, and vorticity. And some of that is driven by our ocean currents. And we've kind of talked about how ocean currents drive climate normals and climate trends. And in our next video, we're really going to dive into ocean currents and their impact on climate. We've talked a lot about the surface and energy budgets across the surface, and now we're going to start diving into some of the local drivers on climate. So things like land masses, ocean currents, etc., that can really impact and drive a climate for a given place. So over here, for example, we could see the Kuroshio current in the Pacific, kind of spinning around just off the coast of Japan along the Tropic of Cancer. We see the California current bringing cold water down from the North Pacific there, kind of along the coast of California. See the East Australia current over off the east coast of Australia, it's aptly named, right? Bringing warm ocean water down from the Central Pacific area. See the Humboldt or Peru current, named after Alexander von Humboldt, but it's also called the Peru one. It kind of driving cold water from the Arctic all the way up the coast of Peru in South America. We've got our Gulf Stream current, which is the one that kind of comes up from the Gulf area along the eastern seaboard, kind of bringing up some warm ocean water along our coast there. Got the North Atlantic drift. We've got kind of a current dissipating out in the North Atlantic as well. We've got our Canary current, which is being driven by water descending from the northern latitudes, being impacted by kind of that Gulf Stream, by the shallower seas there and water coming down. So let's look at some climate change visualizations from NASA and NOAA to kind of put into perspective how some of these things, like surface temperatures, climates, whatnot, really come to interact with one another. So there's going to be a series of 3 videos that I'm going to show. They're each between about 30 seconds to a minute or so. So let's go ahead and watch these together. So here's our first video. So to set this up, we're looking at 5 different graphs here. So we're looking at on the top one. So this is temperature changes or temperature anomalies in the mid-stratosphere. The second one down on the left is from the lower stratosphere temperature anomalies again. The third down from the top is surface temperature anomalies. The bottom is ocean heat content anomalies. And then in that top one right next to me, that is Arctic ice area anomalies. So changes in Arctic ice from 1950 through, I believe it is 2020. So let's go ahead and watch this. So you'll notice on the bottom there is, in the bottom right, there's your legend there. So the gray line, the light gray line, is just observation. So that is our data that we've collected throughout a myriad of different collection sites. We've got the green is natural drivers only, so that would be change that's only driven by natural circulations and cycles. The red is human drivers only, so that's things that we're doing to add heat and energy to the atmosphere. And then we've got the combination in blue of natural and human drivers. So let's go ahead and watch this. You can see these lines starting off pretty constant. Some stratosphere temperature anomalies we can see in those spikes from natural and human drivers, mostly from natural things going on. But around 1950, we start to see everything kind of start to change. We see increases in temperature. We see dipping of the Arctic ice area. 2018 is when this one stops. We see surface temperature anomalies starting to skyrocket that are driven primarily by human impacts. We see the same thing in our ocean heat content. We're seeing that start to spike as well. So if we think about these currents and the distribution of energy and temperature across our planet, heat across our planet, we can start to see that humans are having a pretty big impact on how those things like ocean currents are distributing heat and energy across our world. So let's go ahead and watch the next one here. So this is a more zoomed in look at surface temperature anomalies between 1880 and again, I think 2018. So this was part of a series of videos that came out a number of years back from NASA and the National Oceanic and Atmospheric Administration. So let's go ahead and watch this one. So this is kind of chunked by year. So here we can see between 1880 and 1884, and then it'll progress in kind. So let's go and watch this one. So these are averages over about a 4-year period. So we can start to see, as we're coming into the 50s and whatnot, you'll start to notice a whole lot of change going on. You can see everything is getting this bright yellow and orange color. This one went all the way to 2021. So that's where we are now. So look at those anomalies across the entire Arctic Circle area into Russia, along the Arctic. There are very few areas that serve as cold points or cold anomalies, decreased temperature within our range. So if we think back to what we just looked at, that anthropogenic driver of change is pretty evident in this one. And in the next video, we're going to watch projected global average surface temperatures between 2040 and 2105. So we can see this starting to change, especially areas like Russia and North America, the Central Pacific area, really starting to heat up drastically if we stay on the trend that we currently are on. We're seeing in excess of 8 degrees or more of temperature increase in degrees Celsius along areas like the Arctic Circle. And then finally, this is one of the last ones we'll watch here. So this is going to be annual Arctic sea ice minimum area. So this is kind of the lowest extent of sea ice for a given observational year. We can start to see from 1978 through the present, we can start to see how drastically this is decreasing with, you can watch the visual in the back of what that actually looked like. It was digitized from year to year. You can see we've basically been on a pretty steep decline over the last 50 years. So as a quick recap, in this video, we looked at latitudinal variations in global energy budget, and it really started to dip our toes into some of the drivers of that budget in the anthropogenic sense. So in the next videos, we're going to look at some more of the natural drivers like ocean currents and wind patterns and things like that. And then in the near future, we're actually going to get into some paleoclimate things as well to understand how we know where we are now and how we reconstruct our past climates to get a better idea of what our climate record looks like and how it's changed over millennia. So thank you so much. We'll see you in the next video.